Hello, and welcome to this presentation from Micro-Epsilon. Today I'll be introducing you to one of our optical measuring principles, confocal chromatic, and this is a very real alternative to the more common laser triangulation principle that most people know already. My name is Glenn Wedgbrow, and I am the Business Development Manager for Micro-Epsilon here in the UK. In today's presentation on confocal displacement sensors, I'll be covering the measuring principle, the key differences between confocal and laser, and the typical applications where the technology has been used. Okay, so let's get into confocal measurement and start with some basics. The confocal measuring principle is using the chromatic aberration or separation of white light. White light contains all the colours of the visible spectrum, and when passed through a prism, the individual colours or wavelengths can be separated like the colours of the rainbow. This is due to the fact each colour has a different wavelength, red having a long wavelength and blue having a shorter wavelength, and this results in a different refractive index depending on that wavelength. Now, in most optical applications, the appearance of different refractions through a lens is best avoided and is corrected to give us the appearance of a sharp image, as without the correction of the optics, we would be faced with an apparently unsharp or blurred image. However, it is precisely this phenomena, chromatic aberration, that we use to our advantage with the confocal measuring principle. So, if we have a light source and pass that through a diverging lens, the chromatic aberration or error in the lens will create the spread or rainbow of the individual colours. Understanding the colour returned from the surface of a target can then allow us to determine the distance to that target. Several diverging lenses are used inside the sensor to split the white light before a final converging lens focuses the individual wavelengths to particular positions on the same center axis to give us our measuring range. This also means that the spot size at any given position will be the same as its one particular wavelength of light at each position. To interpret the signal being reflected from the surface, we use a spectrometer located in the controller for evaluation of the wavelength. The white light is passed through the sensor. A particular wavelength, in this image green, is returned through the lens and directed by a half mirror through a pinhole onto the spectrometer. This is seen as a sharp peak of intensity at the particular wavelength returned through the pinhole. Note that the intensity of the peak can change depending on the reflective properties, but as long as there is a peak to be detected, the confocal system can still measure reliably. Of course, other light is also being returned, but based on target position, only the focus wavelength returned from the target is able to pass fully through the pinhole to the spectrometer. The longer and shorter wavelengths are wider at the pinhole, so have much reduced intensity and therefore do not appear as strong on the spectrometer. As the target moves up or down, a different wavelength would be passed through the pinhole. The measuring range of the sensor is then determined by the arrangement of the lenses inside the sensor head. Confocal technology is a real alternative to laser triangulation and is the technology most compared, so over the next few slides I'll highlight some of the key differences. First, let's consider the spot size. With a confocal sensor, because we are separating the wavelengths of light, we have the same spot size through the measuring range. The spot size is also extremely small and can be as little as 3 micron. Laser sensors, on the other hand, actually have a varying spot size, which, depending on the measurement range, is normally focused to the center of the range and is larger at either end. This can be important when scanning over surfaces with differing heights. Also, a laser spot size will typically be around 30 micron at the focus point. When considering how to measure a target, the alignment of the optical axis and return path is more important for a laser triangulation sensor. The orientation of the laser must be considered for when the beam is dropping over an edge to avoid blocking the return signal. Generally, the cone of the confocal sensor allows for measurements up to an edge, and even if one side is blocked, there is still sufficient intensity to take a measurement. Only on very narrow holes in a target where both sides of the cone are blocked does a confocal sensor lose its ability to measure. The second aspect to consider is the surface finish and reflective properties. Generally, a surface will either give a diffuse or direct reflection. With diffuse reflections, you know that some light will be seen by the receiver, regardless of the angle of incidence of the light, and both sensor technologies work well with diffuse targets. When the surface is giving a specular reflection, however, then the laser sensors will either not measure or have to be angled to try and get the light to hit the receiver. In either case, any tilt or change will cause the laser to again stop measuring. Because the confocal sensor is using a circular aperture and the optics are aligned, then specular surface reflections are captured just as easily as diffuse without any adjustments to the sensor. In addition, the larger the sensor aperture, or NA, the greater tilt of a specular target can be allowed. On some of the shorter range sensors, we can operate with tilt angles up to 48 degrees on specular surfaces. The cone of light and optical arrangement means that the confocal sensor technology is ideal for use on almost all surfaces, regardless of whether it has diffuse or specular reflective properties. Laser triangulation sensors can happily cope with changing reflective surfaces, provided that those surfaces are diffuse in nature. By way of demonstration, I've set up the confocal system and without any adjustments, place a range of different targets in front of the sensor. The chart shows the video output signal. Transparent and perfectly mirrored targets are able to be measured also without any adjustment. Indeed, even liquids can be measured reliably, even clear. When a solid object is presented to the sensor, it is easy to understand that the light is reflected back from the surface. When you have a transparent target, you would expect the light to pass through it, and this is generally what happens with a laser sensor, unless there happens to be some marks, dust or grease on the surface that allows a signal to be returned. For confocal, the surface can be completely free of defects. However, as the light enters the transparent material, we have a refractive index change. A bit like when you place a stick or pole in a puddle, it appears to bend. In this case, the focus light in that part of the measurement range is returned back to the sensor. Each transition from one material or medium to the next creates another refractive change, and thus another peak is seen. So now it's possible to measure the thickness with one sensor based on the peaks. The thickness will be the distance between the peaks multiplied by the material's refractive index. However, when measuring the thickness of transparent targets, the refraction index of the material will depend on the focused wavelength. The refraction index changes with the distance between the sensor and the target. If the target is farther away from the sensor, the wavelengths, red light used for thickness measurement, are not the same as with a short distance, blue light from the sensor. When measuring the thickness of transparent objects, therefore, the change of this distance can considerably influence the measurement accuracy. To counteract this effect, Micro-Epsilon has a thickness calibration feature within the confocal controllers to eliminate this effect. The refractive indices, the start of measurement range, the mid-range and the end of measurement range of different materials can be stored in the materials database in the controller. This database can be expanded for other material types and their refractive indices. For maximum measurement accuracy, simply choose the corresponding material so that distance-based errors are automatically compensated for. Thickness calibration is also possible with multi-layer targets such as laminated glass. In order to measure thickness with one sensor, the peaks on the receiver need to be clearly separable. This depends on the resolution of the CCD line and the peak width from the target surface. The larger the sensor's numerical aperture, the sharper the peak obtained. Depending on the sensor used, the minimum separation between peaks we can detect is 5%, so in theory a sensor with a 1 mm range could detect a thickness of 50 micron. And we also have sensors with measurement ranges from just 100 micron. Thickness measurement of transparent multi-layer materials such as safety glass, solar cells, flat screens and smartphone displays can be solved with Micro-Epsilon's confocal chromatic displacement sensors, which are equipped with a multi-peak function. A standard controller can evaluate 2 peaks. A multi-peak controller can evaluate 6 peaks, which enables us to measure up to 5 layers on the respective boundary areas. To accurately determine the thickness of each layer, the controller retrieves the refractive index for each layer from the material database. Each refractive index is corrected depending on the wavelength with the 3 refractive values used for thickness calibration at the beginning, the middle and the end of the layer. Confocal chromatic sensors provide an extremely high resolution. As individual spectral colours are used for the measurement, resolutions in the sub-micron range are possible. Combined with the much smaller spot size than a laser triangulation sensor, confocal controllers from Micro-Epsilon provide a resolution down to 10 nanometers. Linearity of confocal and laser sensors is very similar for a given range, but the sharper, more consistent spot provides a greater stability, which is why the resolutions are so much better compared with laser triangulation sensors. In addition, a laser sensor might have a smallest range of 2 mm, whereas a confocal sensor can be as small as 100 micron. So even linearity can be improved against laser sensors when using the shorter measuring ranges. In terms of sensor heads, at Micro-Epsilon we offer the widest selection of sensors and controllers. Sensor diameters can be as small as 4 mm and can be offered with axial or radial 90-degree measuring direction. Our longest measurement range is 30 mm, and we also offer specialist sensors for use in vacuum applications. Currently, we offer 4 controller types, including the fastest confocal controller worldwide, up to 70 kHz. All controllers feature fast surface compensation, highly accurate thickness measurement due to the thickness calibration, and we have both single channel and dual channel controllers available. The integrated web interface allows for easy setup and configuration, and all controllers can work with all sensors provided they have been calibrated together. One controller can store up to 20 characteristic sets of different sensors. Sensors connect to the controllers via fiber optic cables. They are configured via Ethernet and EtherCAT, and we also support Profinet via the RS422 interface and an additional module. Controllers are powered by 24-volt DC supply. and it is also possible to feed encoder inputs to the controllers for XY scanning applications. Analog output signals of measurements are also available, plus digital I/O for input triggers and alarms. We also offer accessories and mounts, including vacuum feed-through for the fiber optic cables. Just like all optical measuring principles, confocal chromatic sensors require a clean environment. Strong dust, mist and smoke interrupt the beam and allow no precise measurement to be made. However, in contrast to other sensing systems, confocal systems from Micro-Epsilon are entirely wear-free. There are no electronics or moving parts in the sensor heads, and their mechanical stability lasts for years. The light source is the one and only component with limited service life. The sensors are therefore completely passive and they do not give off heat, which makes them suitable for use in sensitive environments such as those with high magnetic radiation and/or explosive areas. In some industries, measurements are needed to be carried out in a vacuum. Confocal chromatic sensors are basically suitable for use in a vacuum. However, all components must be suitable for use in the vacuum. So particularly for use in high vacuum and ultra high vacuum applications, Micro-Epsilon offers confocal chromatic sensors, cables and accessories which can be used according to their respective specification. These models are made from non-outgassing materials, and the production of vacuum suitable components takes place in a low particle clean room. Confocal chromatic measuring systems are used for displacement and distance measurements, but can also be applied for intensity evaluation. Surface properties can be determined to micrometer accuracy using this intensity evaluation. Scratches and slight unevenness can be detected reliably, which would not be possible with just a distance evaluation. The image here shows a flat ground surface. Confocal chromatic measuring systems are increasingly used for fast, distance and thickness measurements. Different sensor and controller models open versatile fields of application for example, in the semiconductor industry, the glass industry, medical engineering and plastics production. Unlike other optical measuring procedures such as laser triangulation sensors, confocal chromatic sensors are less known. However, confocal chromatic sensors stand out due to maximum measurement accuracy and high dynamics while measuring even shiny and reflecting surfaces where laser sensors are operating at their limits. Confocal sensors still have some basic limits, as already explained, so take care and consideration when selecting sensors. And if in doubt, you can always talk to us at Micro-Epsilon for advice on whether confocal sensors can perform well on your target. So let's now look at some of the applications where confocal sensors have found success. Confocal chromatic sensors are used in pharmaceutical and medical technology. An interesting example is the measurement of fill height or level in medical laboratories. Here, active agents are manually filled into micrometer tubes for batch testing. It is essential to measure the quantity of each agent precisely. The confocal sensors scan each micrometer in succession in the plate, and the system measures the distance from sensor to liquid to micrometer accuracy. Miniature sensors with a diameter of 4 mm can be arranged side by side in order to scan the entire width of the micrometer plate. You should also consider the effects of the water surface tension or meniscus layer when making the measurement. As you can see on smaller holders, the meniscus can curve up or down, so typically readings are taken on the center line. In container glass production, wall thickness and roundness of the bottles are crucial quality features. This is why these parameters must be 100% inspected. Any faulty containers are immediately rejected and returned to the glass melt. Due to high processing speeds and in order to prevent the bottles from being damaged, a fast non-contact measurement procedure is required. The Confocal Chromatic Confocal DT2422 dual channel measurement system from Micro-Epsilon can be connected to two sensors and is ideally suited to this measurement task. The system measures synchronously on 2 points of the bottle. Data is output in real time via an EtherCAT interface, and the thickness calibration feature enables precise thickness measurements across the entire measurement range of the sensor, even with varying distance between the bottle and the sensor. Automatic exposure control allows stable measurements regardless of the glass color. In the medical and pharmaceutical engineering industry, plastic ampules are becoming increasingly important. Unlike ampules made of glass, these involve lower risks and can be produced at comparatively low cost as well as in high quantities. The production of medical and pharmaceutical products is subject to strict regulations, which are also included in different standards. Therefore, highest demands for product quality and reliability require continuous inspection of the ampules in order to ensure the patient's safety. In addition to weight and filling volume, the characteristics to be inspected also include the wall thickness of the plastic ampules, which can be achieved with one confocal sensor. Laminated glass, solar cells, flat screens and smartphone displays present a huge challenge for thickness measurement technology, as they consist of several layers and different transparent materials. The exact thickness of each layer and the air gap between those layers must be determined in order to adhere to specified manufacturing tolerances. Due to the high cycle rates involved, the measurements have to be performed quickly and at highest precision. After the assembly process, for example in a smartphone production, it is important to inspect the mounting tolerances of the components in order to achieve continuous quality in all production batches. When manufacturing multi-layer, laminated and curved glass for airplanes, automotive and architectural applications, precise thickness measurement of each layer is important. Confocal sensors master these tasks. If the curvature of the adjacent layers does not comply with the required measurement, there is a risk of increased stress which might lead to delamination of the glass. Confocal chromatic sensors detect the thickness of glass sheets from one side without touching the target in order to ensure a homogeneous thickness profile. Due to their high measuring rate, the sensors are also applied in high-speed processes. Optech Systems is a global supplier of production line laser systems for precision laser micromachining, laser processing and measurements, as well as providing subcontract laser processing services. The company has installed its equipment in most manufacturing environments, from clean rooms to construction sites. Optech has installed non-contact confocal chromatic sensors from Micro-Epsilon on a number of its laser processing machines. These high-precision confocal displacement sensors are capable of measuring the surface finish and groove depth of different materials, ranging from highly reflective, mirrored surfaces to dark, diffuse surfaces. The machines that they build need to work to extremely high tolerances, typically to sub-micron accuracy. This means that any measurement and inspection systems that they install on these machines also need to operate at these levels of accuracy. Confocal sensors are also being used to check the quality and placement of small micro-mechanical parts where alignment and precision are key to the operation of the devices. Here we check the flatness and alignment of the components and the glass face. Measuring the diameters and the dimensional accuracy of bores is possible using special sensors equipped with a 90-degree beam path. Similarly, surface scans of bearing surfaces are also taken using confocal chromatic sensors from Micro-Epsilon. In coordinate measuring systems, spatial coordinates of points on a workpiece surface are captured. These measuring points are further processed by a computer, and the values of the selected geometric quantities like length, distance, angle are calculated. Such machines can be used to check whether workpieces comply with the designer's specifications in terms of their geometric shape. The confocal chromatic measuring systems from Micro-Epsilon are used when surfaces and materials with different curvatures, such as gears, external threads, are to be measured without damage. They are ideal for this purpose, since their high numerical aperture enables high resolution, large tilt angles, and a small light spot. In electric car battery production, the thickness of the materials that make the battery plate are critical to the amount of charge and efficiency the final battery cell will have. Early detection of thickness variations in the wet coating applied to the base material help ensure product quality. The glossiness of the surface is no problem for the confocal sensor. Here we see an application where confocal sensors have been implemented by Micro-Epsilon's own systems division. In this application, a confocal system is used in a leveler line, which is making the strip flat after rolling. The material here is highly polished, but the confocal system is able to measure the thickness to plus or minus 0.7 microns. Apart from its accuracy and ability to measure shiny surfaces that lasers would struggle with, the confocal system is also able to detect multiple transparent layers. So, for example, where oil is present, the first signal peak can be ignored to ensure the correct thickness value is taken. Confocal technology is available on Micro-Epsilon C-frames up to a traversing width of 1 meter with measurement ranges up to 20 millimeters. The installation shown here is on a copper coil line. The copper is extremely shiny and is used for electrical cabling. The key parameter for the customer here is the frequency of the thickness deviation along the center line of the material, and we use a fast Fourier transformation to output the required frequency value. So to summarize the key points for confocal sensors, they're capable in measurement as any laser triangulation sensor. The controllers and sensors are industrialized for use in automation and production control. The confocal technology is able to measure almost any surface without change, including mirrored and transparent targets, even liquids. The chromatic aberration principle and optics ensures an extremely small and constant spot size and leads to nanometer resolutions. And the sensors are completely passive, so can be used in applications where powered sensor heads are not allowed. That concludes our introduction to the confocal chromatic technology from Micro-Epsilon. If you want to keep up to date, you can follow us on LinkedIn, or if you go to our website, you can subscribe to our newsletter with regular updates about product information and applications. Thank you for watching.